In this video, we're going to discuss electric field lines, what they are, how to interpret them, how to use them. Now, electric field lines are an alternative way of showing the electric field at all locations. Now, since electric field is a vector, the traditional way you would show it is by showing vectors at all different locations, sort of like if you showed the arrows representing the direction and speed of wind everywhere on a map. But it can get confusing to have several of those, and there's better ways of showing it. Now, an example of a set of electric field lines is this picture, where the red lines are the electric field lines showing you which way the electric field is at each of these points. Now, in this interpretation, the direction is the easiest thing to see. Here, the direction is just tangent to the lines. It's always tangent to the lines. So, for example, in this last slide here, the field is always going to be, for example, along here, downwards, because that is the direction that's tangent to this location. Down, 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 down. And the arrowheads here in the middle are showing you whether you should be doing down or up. Over on this location right here, the electric field would be either up and to the right or down to the left, depending on the arrowhead. Since the arrowhead is flowing through this way, the answer is down and to the left. So you draw an arrow like that. But the question would be, well, how long is the arrow? Or more technically, what's the magnitude of the electric field? Where is it stronger and where is it weaker? And it turns out the answer is it's proportional to the number of lines, the density of the number of lines. So the areas where the lines are close together are areas where the electric field is very strong. Areas where the electric field lines are very far apart is where the electric field is very weak, and you have short arrows. I'm going to have an example where I'll just draw electric field lines in red. And here, what we're going to have is a simple case where we have a field line that runs to the right, and I'll add a couple of the field lines. Now these don't really begin or end, I just have a finite amount of space on the page to draw them. And all of these here are, if you can't tell, it's supposed to be arrows indicating that the electric field runs in that direction. Now, what I'll do is show you what the electric field lines would look like for that arbitrary set of electric field, what the electric field vectors would look like for that arbitrary set of electric field lines. If I can get this to work. I will draw the electric field vectors in black. Now, let's choose a point here. Here, the vector is going to be in the same direction as the line, which is up and to the right. And I'll choose the length of it arbitrarily, just a length I can show easily. Down here, it's going to be in a different direction. Now tangent is slightly shallower, so more like that. And the lines are denser here than they are out here, so I should draw this as a longer arrow. Now it's hard to show exactly how long it is, but that would be a rough approximation. The electric field here would also be then to the right, same direction as the lines. In here, there would be the same length because the density is the same in here, comparing, say, early on to later on. And all these arrows are supposed to be straight arrows. Again, I just can't draw very straight on this program. So the black would be showing you the electric field vectors, the red would be the lines. The direction is again easiest, but the magnitude can be seen by how close the lines are together. So let's do a side-by-side comparison of this. For the field lines, it's easy to tell the direction, it's sometimes easier to remember what they look like, and it's usually easier to estimate what the field lines look like, but it's more difficult to look at exactly what the vectors would be. So why would you use field vectors? Well, for field vectors, you you can easily tell the magnitude, which is hard to do, at a couple specific locations. So if you want to find the show the electric field, say the example of we have a 4 at the location of an electron or some other charged object because you want to find the force, usually you draw the vector. The other really nice thing about it is that you can add up electric field vectors in order to find the total electric field. But you can't add electric field lines. I know of no way in which you can take two sets of lines and put them together to find the total electric field just using the lines. So, what you usually have to do is if you want to find the total electric field is you have to use electric field vectors. They're both showing you the same information, the electric field, and I will use both of them, but there are two different notations for showing it. Now the rules you want to be using whenever drawing the lines are as follows. First off, your line should always start on positive charge, and they'll always end on negative charge. So just like this example I showed earlier, I'll flip back to it. These red lines are the electric field lines. Here they start on the positive charge, which is what's on top, and they end down here on the negative charge on bottom. And they all start here and they all end there. Now how many lines start or end on a given charge is proportional to that number of charge. And that proportionality constant, you're free to set whatever you want to be. For example, say I have 3 microcoulombs of charge. I could choose that to represent that using 6 lines coming out of there, 3 lines coming out of there, 9 lines coming out of there. But the ratios should be appropriate. So if I had a positive 3 charge, positive 3 microcoulombs to use a relevant unit, and a negative 6 microcoulomb charge, and I had 3 coming out of one, I should have 6 ending on the other. That should be the correct ratio. It could be 6 out on one and 12 in on the other. It still has to be a factor of 2 because there's twice as much charge. Now, in your drawing, you don't have a balance of charge. You don't have just as much positive as you have negative. Then you'll have either more lines starting on positive charge than end on negative, or more ending on negative than start on positive. So you'll have lines that don't either begin or end in your drawing. And the way you usually phrase this is that those lines just run off the edge of the page and you say that they connect to infinity. Well, really they don't connect to infinity. There's just some other page that is some other charge that's off the page that you aren't showing that it does start or end on. But that line came from somewhere or ends on somewhere, and it just happens to start or end on the charge in your picture. Now, another thing is that your lines will never cross. And the reason why is because the electric field is supposed to be tangent to the electric field lines. If the lines cross, then at that point there are 2 different directions the line is pointing in, which would mean the electric field will have 2 directions, which you can't have a vector point in 2 different directions. The other thing is that the lines would be infinitely dense at that point, because 2 lines would occupy 0 space. And if you have an infinite density of lines, you would have an infinite magnitude electric field, and you physically can't create an infinitely large electric field. The last thing is that whenever you make this, the lines should generally curve smoothly, so that it'll curve, and there tend to not be any kinks in electric field lines. So you can sort of guesstimate how to go from the beginning to end to curve smoothly from one to the other. And the last note is that you should always draw your electric field lines as having arrows in the middle to make sure you're not confusing it with electric field vectors, which have arrows on the end. And if you accidentally draw it on the end, it's not the end of the world, but it can be hard to tell if you really just meant the electric field pointing in one direction and was that long, meaning the magnitude was that long, or if you just meant that here was a line you were drawing and you're trying to show the direction just across that curve. Note, vectors will never be curved. Electric field lines are almost always curved.